Hi there! This series covers the first 100 Project Euler problems to help you learn how to solve unfamiliar problems. Project Euler presents complex math challenges to be solved with programs running in under a minute. Although they prohibit sharing solutions, the first 100 problems can be shared for instructional purposes. I encourage you to attempt each problem on your own before watching the corresponding video. I am currently learning Python and have been doing so since mid-January. I have no professional experience in the language and have only completed the Python for Programmers course on Execute Program. While I'm learning quickly, I don't claim any real expertise. Today, we're looking at the 57th Project Euler problem. As always, I will link to the problem and my repo in the description. Let's dive in. Problem 57 is square root convergence. It is possible to show that the square root of 2 can be expressed as an infinite continued fraction. So square root of 2 equals 1 plus 1 over 2 plus 1 over 2 plus 1 over 2, etc. By expanding this for the first 4 iterations, we get 1 plus 1 over 2 equals 3 over 2. 1 plus 1 over 2 plus 1 half equals 7 fifths, etc., etc. The next 3 expansions are 99 over 70, 239 over 169, and 577 over 408. But the 8th expansion, 1393 over 985, is the first example where the number of digits in the numerator exceeds the number of digits in the denominator. In the first 1,000 expansions, how many fractions contain a numerator with more digits than the denominator? Okay, so the hard part of this is going to be figuring out the pattern here. And to help us with that, I'm going to pull up Paint. So obviously this first case, pretty trivial. Let's jump down to this 4th iteration so we can kind of see the pattern emerge. So I'm just going to draw this out here. Okay, so 2 plus 1 over 2. 2 plus 1 over 2 is easy. We take 2, multiply by 2, add a 1, so it's 5 over 2. So this becomes 5 over 2. And then 1 over any fraction is just that fraction upside down, so it becomes 2 fifths. And then 2 plus 2 fifths is going to be 2 times 5, which is 10, plus 2, which is 12. And then an 1 over that is going to be that reverse, so 5 twelfths. I'm going to start writing this a different way. 1 plus 1 over 2 plus 5 twelfths. And then, again, 2 plus 5 twelfths is relatively trivial, so 1 plus 1 over 24 plus 5 is 29 over 12. And then we end up with 1 plus 12 over 29. 29 plus 12 is, in fact, 41. Yes, so we can kind of see here, by doing this math and looking at these patterns, 3 plus 2 is 5. 7 is 5 plus 2. 5 plus 7 is 12. 17 is 12 plus 5. 12 plus 17 is 29. 41 is 29 plus 12. So we have this pattern emerging here where for any given number in the sequence, it is, let's see, let's draw this up as n equals x. Okay, that's silly. Let's just say for any given n. So n equals... Okay, let's just call it x. Sorry. So x, any x is equal to, let's see, the numerator plus denominator for x minus 1 under the numerator plus the denominator plus the denominator for x minus 1. So we can kind of see this pattern, and it shouldn't be very difficult for us to program this pattern in. I'm going to move this onto another screen, just so that it stays visible to me. Unfortunately, it will not be visible to you, but we're going to copy it into our file right now. So this is problem 57. Each expansion x equals num plus denom of x minus 1 divided by num plus denominator of x minus 1. So, gonna go steal our favorite two lines. Oh goodness. So we actually haven't used together in a while. Okay, so I'm gonna go ahead and do a limit equal to 5. And then I am going to do fractions is going to be a list. And I am going to print fractions for right now. So what we're going to do is numerator is equal to 3. Denominator is equal to 4. I'm sorry, 2, because that is the first one. Not sure I've spelled denominator correctly, but I don't think that matters whatsoever. And then for I in range 2 to limit, let's see. Actually, I'm going to start this fraction off. So it's 3 over 2 is our very first one. New num equals numerator plus denominator. Sorry. New denominator equals that, and then new num equals new denominator plus denominator. And then we're going to do fractions dot append of this tuple. then set numerator equal to new num and denominator equal to new done. Actually, yeah, I'm just going to do it this way. So, obviously this doesn't actually answer the question because the question wants us to compare the number of digits between the numerator and the denominator. But for right now, we're just doing a proof of concept. So we want to make sure that, like, we've got the correct answers. So we get 3 over 2, 7 over 5, 17 over 12, and 41 over 29. 3 over 2, 7 over 5, 17 over 12, and 41 over 29. There we go. So we're getting the correct answers so far. If I increase the limit to 9, the last one should be that 1393 over 985. There we go. Okay, so we're calculating the correct values here. So all we need to do now is maybe instead of appending these fractions, or let's do an addition to for right now. So now let's say if length of string numerator, I don't need these parentheses, this is not Java. Length of string denominator then count plus equal to 1. And then we just print out that count. So with the limit of 9, obviously we should only see 1 as our count. And we do. So now we no longer need to be saving this, and we no longer need to be printing this, which means we no longer need that. And if we increase our limit up to 1001 to account for the fact that, like, we got to go all the way through 1000, then it gives us the number 153, which I am willing to bet is the correct answer, unless I have an off by 1 error. It is the correct answer. Alright. So, there, again, the hardest part was figuring out exactly what the pattern is. Once you figure out the pattern, it's very, very easy to translate that pattern into code and run through it. So, that's it for today, and I'll catch you in the next one.